Hello everyone, welcome to the recording on inferential statistics. In the previous two recordings and the two recordings prior to that, right, we focused on Spark, we focused on machine learning, the basic machine learning, right, and then now what we're doing is we're focusing on deep dive into statistics, right. In the first statistic recording, we were looking at descriptive statistics, central tendency measures, right? And then in the next recording, in the previous recording, we looked at how we use central tendency measures and the variability measures to solve the crisis in Beaufort. Right? So now in today's recording, we're going to look at the second branch of statistics, as we already saw, right? What is the first branch of the two branches of statistics, right? Descriptive statistics and inferential statistics. Descriptive statistics is by far what most people know, most people understand, right? Now we are looking at inferential statistics, right? Drawing conclusions about the population based on sample data. So that's the branch of statistics we are going to dedicate this recording to, right? Let us get right into it. With an example, right? Similar to the Patrick's problem, we are looking at another problem where statistics is going to solve in real world. And this problem is about a little girl called Sarah, right? Sarah is a student of English literature, okay? She is part of a class of 50 students, right? And here is the deal. Her English teacher said that she will give Sarah a scholarship only if she is in the top 10% of the class, right? Only if she's in the top 10% of these 50 students, right? And Sarah prepared hard and she scored 70 out of 100. Now she is anxious to know whether she's in the top 10% or not, right? Her score is 70, right? And she came to know that the mean of all the 50 students is 60. Standard deviation is 15, right? But Sarah is not really happy. She's still anxious because she knows that she's better than the mean. That is fine, right? She's better than 50%. But that's not the deal, isn't it? She will receive the scholarship only if she's in the top 10%, right? Now, how well did Sarah perform in her literature work? So what do you guys think? Is Sarah missing a statistic? Did she already get the scholarship? Or do you guys need more data to find it out? Or with just this data, can you tell me whether Sarah received scholarship or not, right? What is happening here? What is the problem that I'm asking you guys to solve? Can you infer from this data on where Sarah stood? Inferential statistics, right? So this is the biggest contribution of statistics to data science, this particular branch. Inferential statistics generalizes the large data set and applies probability theory to draw a conclusion, right? As you can see here, this is a large data set. Okay, from that, you take a sample, smaller data set, and then you apply the concepts from probability, right? And then that helps you make sense of the data, right? What exactly is the data set telling you? Right? What kind of inferences can you draw from the data set? That is exactly what data science is, isn't it? Right? So that's what inferential statistics is trying to do. Drawing inferences, right? Another real world example. You have only 100 agents data. Average worth of insurance sold by 100 insurance agencies, $179,322. That is nothing but, as we saw, as we discussed in the previous recordings, right? Because it's a parameter, it's a data point about sample, it is called statistics, sample statistics, right? From this, can you infer more about the general population, all the insurance agent guys, right? Can you infer more from this? The best guess of the insurance sold by 10,000 agents would be 179,322. You are extrapolating this inference. You have this data, 100 agents, which you feel is good enough, right? Based on that particular value, you are inferring what the general population is going to be. Is this an accurate value? Not by a million miles, right? but somewhere in the ballpark number. That's the whole idea of this inference. Similar to how many families in India have a household, have multiple TVs. How many households in India, right, have multiple TVs? Within your neighborhood, right, you researched and you found that out of 50 families, only 10 of them have multiple TVs, right? So you will infer that even across all the families in India, only 20% of them, because 10 by 50 is 20%, right? Only 20% of them will have multiple TVs. Is that an accurate estimate? Who knows, right? But that's a ballpark number that will help you in taking business decisions, right? If you are a TV manufacturing company, you know who to target now, right? So now these inferences that you're calculating, you're drawing, instead of directly applying these values as it is, right? 179 or 1 by 5 and everything, can I use probability? The one word that used to strike fear in my heart when I was first understanding probability, when I was preparing for these competitive exams like GMAT, CAT, right? There's one concept that always scared me, right? But the more time I spent trying to understand it, the more I was able to appreciate why it was so scary at first, at the same time, so important when it comes to all these competitive exams. So let us try to understand probability in simple terms. Before that, I'll ask you a question. Depending on the time of the day you are watching this recording, right? It's a nice hamburger, yummy hamburger. What is the probability or chance that this hamburger will weigh exactly 0.25 pounds? What is the probability or chance that this hamburger is going to weigh exactly 0.25 pounds? Take a second, right? And then give an answer. Forget about probability. Maybe you don't even know probability. Just talk about chance. The way you're going to talk about India's chances of winning a match, 50-50, 60-40, 80-20, right? Apply the same logic to this and tell me what is the probability of this hamburger weighing exactly 0.25 pounds. The answer is 0. How many guys are surprised by this? The guys who are surprised, right? You need to pay attention to the word exactly and the fact that it's a continuous variable, right? 0.25. You guys remember the bowling speed example? Was it discrete? No. It is continuous, right? It can take any values, any decimals, right? And a hamburger weighing exactly 0.25 doesn't happen, right? That's the reason why the probability of you finding a hamburger that weighs exactly 0.25 pounds is 0. So now what is this probability? What is this chance, right? In its simplest definition, estimate how likely something is to happen, right? How likely is it going to rain tonight, right? How likely is you obtaining a ticket to Avengers Infinity War on its first day? How likely is it for Arsenal or Chelsea to win the Premier League? How likely is it for the stocks to rise? How likely is it, are you going to have a boy or a girl, right? All these are talking about chances. So probability is nothing but chance. In other words, probability is nothing but random chance. Random itself means chance, right? So how do we calculate these percentages? We draw on previous experience to determine how likely something is to occur. We look at the previous occurrences, right? Previous data points, and then we say, out of 10 days, like today, 4 days it rained, right? 4 by 10. Chances are 40%. Out of 10 movies that I watched, after 10 Marvel movies I watched on first day, right? I was able to get only ticket to 6 of them. Rest of the movies I watched on the second day or the third day, right? 6 by 10, 60%. Out of 7 years, out of 10 years, right, when Premier League happened, 7 times Arsenal won when match between Arsenal and Chelsea was played. 3 times Chelsea won. So the chances of Arsenal winning is 7 by 10, 70%. Out of 100 stocks that I hold, right, the chances of a particular stock rising is 70%, something like out of 100 of these days, right, similar days in the past, the stock has rose on 70 out of this 100 days, right? So now the chances of this stock rising are 70%. If you see, this is nothing but machine learning, right? You are passing judgment based on historic data, right? Boy and girl, right? Always there is a 50-50 chance, right, of you having a boy or a girl, right? So the chance is 1 by 2. The 2 possibilities, and you're interested in one possibility, which is either a boy or a girl. So the probability is 1 by 2, which is nothing but 0.5. Now, if you observe this closely, you will find that there is a pattern, there is a formula emerging. What is that formula? In the denominator, you have all possible choices. 100, 10 days, right? All possible events that are of interest, that are possible, right? In the numerator, you're only talking about events that are of interest to you. In this case, Arsenal. In this case, stock rising. In this case, either a boy or a girl. In this case, you watching a movie on the first day. In this case, a day on which it rained, right? So numerator contains the events that you are interested in. Denominator contains all possible events. Take another example. Throwing a dice. What is the probability or chance of you getting a 1 when you throw a dice? Let us look at the formula, right? Denominator contains all the possibilities. How many possible values can you get? Discrete, right? 6. There are 6 faces in a dice. It's a cube, right? And in the numerator, the possibility that you're interested in. What is the possibility that you're interested in? 1, right? So 1 by 6. That is the probability of you getting a 1 on the dice. Why is probability so essential? Probability is the foundation and the language needed for most of the statistics, right? That's why we're spending so much time understanding probability. It will incorporate certainty, right, into decisions derived from statistics, right? Your big decisions, your credit score, your loans, right, they get approved based on probability. If they look at your historical data, right, if the credit score is good, then there is 70% probability of you getting a loan, right? Probability is everywhere. Probability is ruling the roost, as they call it, when it comes to machine learning, right? And the range of values for a probability, again, we are looking at range, all possible values, right? They lie between 0 and 1. 0 is when it is impossible. When will the value be 0? Right? When the event that you are interested in doesn't just happen, right? What is the probability of you running into a dinosaur, right? Out of all the animals that you can run into, which is nothing but the denominator, what is the probability of you running into dinosaur, right? The numerator is 0 because dinosaurs don't exist. The reason Jurassic World movie is a great movie, is an awesome movie, right? But then still, it's a movie. Dinosaurs just don't exist, right? Dice, we already discussed it, 1 in 6 chance, right? Unlikely, again. Predicting it. Even chance, just like boy and girl, heads and tails. Likely, the probability increases, right? 4 out of 5. Right? 5 is the total number of possibilities, and 4 are the possibilities that you're interested in, 80%. Certainty, right? That means you are interested in certain possibilities, and they are the only possibilities, right? You always want your odds or a probability to be closer to 1, right? That's where you are taking the guesswork out of it, isn't it? Right? Safe option. The probability is when 1. What does that mean? You can safely go ahead with your judgment, right? So now let us look at calculating the probability for coin toss, right? So what I would recommend you guys to do is, after this particular recording, if you have time, if you have some spare time, take a 1 rupee coin or a 10 rupee coin or any rupee coin and try tossing it at least 30 times. Okay, and then record the number of times you have head and number of times you have tails. Right? And you'll surprisingly find that the number of heads and number of tails will be almost equal. Right? In one of the previous batches, one of the students who did that, he did it for 70 times, and he found 34 times he got heads and 36 times he got tails. Right? What does probability mean? When I say the probability is 0.5, what does that mean? If you throw the coin 100 times, 50 times you will get head, 50 times you will get tail. If you repeat this experiment of throwing a coin or throwing a dice 100 times, right, you'll get 50 times head, 50 times tail, 50 times tail. You'll get one at least 17 times. It is round about 16 or 17 times, right? As I said, statistics is all about approximation. It's not about accuracy, exact values, right? If you throw a dice 100 times, 16 times you'll get one. You guys can give it a shot, by the way, right? Now let us understand how we are calculating these number of heads when you're flipping a coin, right? Let us take, so here in this particular picture, it says first coin, second coin, third coin, but read it as first throw, second throw, third throw of the same coin, right? I'm throwing the coin first time. It will be either a head or a tail, right? I'm throwing the coin again. It will be either a head or a tail, and again, head or tail, right? So the possibilities, if you consider the first coin and first throw and the second throw, or it can be both heads. First time when you threw, it is a head. Second time when you threw, it is also a head. Or it can be first time head, second time tail, or first time tail, second time head, first time tail, second time tail, right? So how many possibilities were there? 4. You throw the coin again, third time, right? Now it can be head or tail. And now if you look at the outcomes, these are all the possible outcomes, right? Triple H, double HT, HTH, HTT, THH, THT, TTH, and triple T, right? These are all the possible outcomes. If you just look at the outcomes of a coin thrown 3 times, right? So now what I'm doing here, I'm representing it, right? X equal to number of heads after 3 flips of a fair coin. Remember what is X? X is nothing but a random variable, right? What is a random variable? A variable that denotes an event, right, where you don't know the outcome. Do you know the outcome of number of heads in advance? How many times you'll get head when you flip a coin 3 times? Nope, nobody knows, not even God, right? So that's the reason why we represent that with X. And here, probability of X equal to 0. What does this mean? What is a probability chance that I don't get any heads after flipping a coin 3 times, right? What are the total number of outcomes? 8, right? What is the only outcome where I don't see a single head? That is this, tail. All 3 being tails, right? So that's exactly the outcome that I'm interested in, which is 1 by 8. Second one, probability of X equal to 1, right? What is the probability the number of heads is equal to 1 after 3 flips of a fair coin, right? Let us see what are all the outcomes where head is repeated only once. This is 1, this is 1, this is 1. So these are all the possible outcomes, 8, right? And the outcome that I'm interested in is 3. The value is 3 by 8. X equal to 2, right? Heads equal to 2. Number of times 2 heads came, this one, and this one, right? 3 by 8. X equal to 3, all 3 times head, only this, right? So that's the reason why the output is 1 by 8, right? Now if you want to calculate the probability after only 2 flips, forget about the third flip, only 2 flips. If you look at it, right, probability of X equal to 0 when there are 2 flips, how many possibilities are there? HH, HT, TH, TT. How many possibilities are there? 4, right? Number of times probability of X equal to 0, again 1 by 4, X equal to 1, head equal to 1, right? 2 by 4, right? X equal to 2, 2 times head, right, which is 1 by 4, right? Do you see a pattern? When you throw the coin 3 times, number of possibilities are 8. When you throw the coin 2 times, number of possibilities are 4. Similarly, when you throw the coin 4 times, number of possibilities will be 16, right? So what does this say? The number of possibilities of you throwing a coin, right, is always going to be 2 to the power of n being the number of flips. Okay, so this is how you calculate probabilities. Okay, now let us, so this is nothing but discrete values, right? These are all discrete values. If you look at it, number of heads equal to 0, 1, 2, 3. So these are all the possible values for random variable x, right? Number of heads cannot be 1.5 or 2.5, right? So these are all called discrete values. So if you plot them out as a probability distribution, so probability distribution of our event, right, then the value of x is going to be 0.13, that is nothing but 1 by 8, right? 1 by 8, 3 by 8, 3 by 8, and 1 by 8, right? X value is on the x-axis, right? 0, 1, 2, 3. Okay, so that is how you plot it. So now if you see, you are slowly able to see a bell curve, a histogram, right? Something that resembles a bell curve, isn't it? Right? We are going to see this in more detail during our rest of the discussions. Right? But remember, this is called probability distribution of our event. What is our event? Throwing a coin 3 times. Okay. Now, what if the possible values are like hamburger? Right? In the case of number of heads, the values are integers 0, 1, 2, 3. What if I'm looking at number of values as continuous, just like the speed of balls delivered by a fast bowler, or the weight of a hamburger, which can be continuous? In that case, the function will no longer be just like this discrete bars, right? It will be a continuous function such as this, right? Probability density function. And you see, the interesting part is that some of the values are less frequent because the y-axis talks about the frequency of occurrence of these values, right? Here, that is the case, right? Here, 0.13, the y-axis value. What does it talk about? The frequency with which you will see number of heads being 0 when a coin is tossed 3 times, right? Here is the same case. You see the probability hitting the peak at 0.5. That's a perfect normal distribution curve. We are going to discuss normal distributions in the next recording, right? But this is symmetric. This is how a probability density function, a continuous probability density function, looks like. Right? P of x equal to 50 is equal to 0. How are you going to calculate the area of a line? What is the area of line? Area of line is 0. Why? Because line has only one dimension, right? Here, this line, the area of this line is 0, right? But whereas if you want to calculate the area within boundaries, right? Say, for example, go back to our earlier question. What is the probability that the hamburger weighs exactly 0.25? Instead of that, if I ask the question, what is the probability that hamburger is going to weigh between, say, 0.1 and 0.3 kgs? Then what you will do, you will calculate this area, right? The area between these lines, right? And that's the reason why you're always going to get a value when the question is between a range, right? The reason for that is continuous. It's continuous distribution, right? You cannot never be completely perfect. Right? You can always say the speed of a ball is going to be between 85 and 86 miles per hour. That's a valid guess, right? That's a valid probability. We can calculate the probability of doing that, right? But you can never say exactly, because it's a continuous value. It's a floating point number. You can't come up with an exact value, right? As you can see from this particular data formula, don't be intimidated by the fact that you see an integral here, right? The probability of probability of a hamburger weighing between 49.9 and 50.1, you calculate this area, right? Integral, what it does is it calculates the area with all these values that are spread out. That's the reason why it is an integral. 50.1, 49.9, p of x into d of x, right? So don't worry about the formula, but just remember that if you calculate the integration across all these values, you're going to get the area of this particular part, right? So this is how a continuous distribution function is plotted. Okay, now let us look at probability values when it comes to population, right? So survey for job prospects in New York University, population, right? The population is students at the university, right? Exchange students, students enroll for correspondence, students at home, students who have graduated, who have just graduated. So all this, right? So what your job is to survey these people, these different categories of people for job prospects in New York University, right? Now what you do, you can't survey all possible students because there's just so many students. What you take a survey, right, from students who are now present in the university campus in the canteen. You can't ask all the 550 or 1,000 students in Stern University to come to one place and then you ask their job prospects, right? What you do, you find people who you can easily reach out to. Small gathering, right? A sample. Yes, you take survey from students who are now present in the university campus in the canteen, right? So that is nothing but sample space, right? The sample that you take to conduct your experiments is nothing but sample space. And event is nothing but the likelihood of getting even numbers. So this is sample, right? All possibilities in a sample, right? And the event is nothing but the likelihood of you getting even numbers. So one particular point in the sample space is called sample point, right? So now let us look at some of the terminologies. I want you guys to be familiar with these terminologies. An event is nothing but an occurrence, right? Look at this example. A client agrees to invest in mutual funds in the company, right? This is an event. The complement of this event is a client does not agree to invest, right? So complement of an event is nothing but a non-occurrence of the event, right? The occurrence where the original event doesn't happen, the absence of earlier event, that is nothing but the complement of an event, right? So generally what you do when you're trying to make decisions, you make decisions using a tree-based approach, right? You want to buy a new car, right? Whether you want to buy a sedan or do you want to buy a hatchback? Do you want to buy a standard car? Do you want to buy a luxury car, right? You take a decision based on type of car, the color of car, and then maybe some other parameter, right? So you always build a decision tree, right? You draw a tree diagram, right? And you count the total events, all possible events, right? You are looking at the different colors, you're looking at what kind of car is it, luxury car or standard car, right? And then accordingly, whichever event has the highest chance, right, is the most preferred, you go with that option. Maybe this is more economical. Blue hatchback, blue sedan, right, is more economical. You prefer this particular direction tree, right? In which case you take a decision based on that, right? So that is where you are always, whenever you're making decisions using probability, right, you're always in your mind, you are creating these decision trees. That even same applies when you are accepting a job, right? You look at various things like package, variable pay, location preferences, work culture, host of parameters, right? And then only then you make a decision, right? The same way you draw a tree diagram, decision tree, and you make a decision, right? Now another thing called independent events, right? So one person A visiting a movie theater in India, person B visiting the Cineplex in Australia are two independent events. Why are they independent? When are these events called independent? They are not dependent on each other, right? What does dependency mean? This guy, say your friend going to a movie in Australia, right? He's not going to a movie in Australia because you're going to a movie in India, right? He has not made the decision to go to a movie in Australia because you went to a movie in India. There can be friends like that, right? But let us assume in this particular case, we're talking about sane people, right? Who are basing their decisions based on their personal interest, not based on what others are doing, right? In that case, they're called independent events. We just wish our life to be full of independent events, isn't it? But they seldom are, right? Most of the cases, you will be taking decisions because of what others around you are taking. Be it, right? At least I took decisions in that manner, right? I took engineering because most of my cousins, most of my friends are taking engineering. I took computer science because I was looking at my friends moving towards computer science, right? I joined Bank of America because most of my friends who got placed in Bank of America, they accepted that offer, right? At least I always tend to follow the herd. Even if I don't want to follow the herd, ultimately it so happened in my life that I always followed the herd, right? And that is me taking all the dependent decisions, right? All the events, right? They are not independent. All the decisions that I've taken, they're all dependent decisions. They are dependent on somebody else doing something, right? And that is the case even now, right? So whenever, if you're looking at examples like people, your relatives or your friends, right? They always compare you with something else, right? They always want you to do something because someone else is doing the same thing or someone else is not doing the same thing, right? In which case, they want you to stop that and do the thing that other person is doing. Something like going to US or going to Europe, right? Settling abroad, right? It's not because they feel that is the best thing for you. It is because they want you to better what other person is doing, right? These are all dependent events, if that is the case. But independent events are events where you are going ahead and you are taking a decision by your own, right? Those kind of events are called independent events, just like this particular case. Dependent event, another classic example, the spike in sales of umbrellas in Walmart is dependent on rains and thunderstorm. So whenever there is a thunderstorm outside, there is a spike in the rainy season, right? Number of umbrellas. What does that mean? The event of umbrella sales increasing is not independent. It is dependent on an external event, which is a thunderstorm, right? That's what the independent and dependent events mean. Now we look at another interesting terminology called mutually exclusive events, right? In a Walmart store, the sales of sports equipment is mutually exclusive of the sales of grocery. Is that true? Right? So what's the difference between independent event and mutually exclusive events? Right? So mutually exclusive events, there is no relation, right? There is no relation, something like, at least in independent events, right? You are still going to the movie, both of you, right? And it is still, there is some relation that one person is a friend of you. You're just taking the decision independently. Here, there is no relation, nothing whatsoever, right? The sales of sports equipment is mutually exclusive of the sales of grocery, right? So that is called a mutually exclusive event, right? Now let us see how we calculate the probability using historical occurrence, right? So let us look at this particular data that is in front of us, right? So if you look at the data here, laptops sold, right, is on the leftmost column, right? And number of days is on the rightmost column, right? And then we have in the first day, not a single laptop was sold, right? And then in the second day, one laptop was sold, right? And then in the third day, in the first 10 days, right, two laptops were sold. And then the laptops 5 or more, right? It's a pretty sad business if you look at it, right? This number of laptops sold even after a total after say 12 days is only 17 days is only 4, right? Now what we are doing here, probability of selling laptops on any given day is 2 by 30. So what is 30? Total number of days, right? So probability of you selling laptops on one laptop on any given day, right, is 2 by 30. How many days did they sell at least one laptop? 2 days, right? They sold one laptop. So what is the number of days? 2 by 30, 0.07. The probability of you selling 4 laptops on a single day is 5 by 30, 1 by 6. 5 by 30, which is 1 by 6, which is close to 0.17, right? And based on past history, can you say that you will sell at least 5 laptops on any day? No, you don't have the confidence because that never happened, right? The probability is 0 by 30, right? You can never say that based on past history, right? 3 laptops will be purchased in a day, right? So these events, right, as you can see here, right, these probabilities give you some insight into the future, right? So here on 12 days, 3 laptops are sold, right? On 5 days, 4 laptops are sold, right? On only 1 day, not a single laptop is sold, and there is no day where 5 or more laptops is sold, right? So this is not a sad business as we initially thought, like I misinterpreted the data, right? It's a good business, right? So on 12 days, 3 laptops are being sold, right? And on 5 days, 4 laptops were sold, right? So that is how you manage the inventory using probability, right? And as you can see, probability of any event, these are the rules of probability, is between 0 and 1. And if you sum up all the probabilities, you will get the value as 1. Why? Because denominator is the same if you sum it up, right? And numerator, what is numerator? Numerator is nothing but the number of events that you're interested in, right? And denominator is nothing but all possible events, right? And the number of events are, if you consider all the possibilities in the numerator, you're going to get the denominator, isn't it? If you summarize it, right? So that's the reason why the sum is 1, right? Now, what we are going to do here is we are going to extend the problem statement, so make it a bit complex. What is the probability that a customer visiting the store buys at least a laptop or a pen drive, right? I'm going to give you the probability of them buying a pen drive, but here I'm interested in not just buying a laptop. I'm interested in finding out what is the probability that a customer visiting the store buys at least a laptop or a pen drive, right? So before this, you need to understand the difference between mutually exclusive events and independent events. Mutually exclusive events cannot happen at the same time. Are these mutually exclusive events? Can you buy laptop and pen drive at the same time? Yes, right? These are not mutually exclusive events because they can happen at the same time. Whereas events are independent if the occurrence of one event does not influence the occurrence of other, right? Which is nothing but you buying a laptop is not influenced by you buying a pen drive, and you buying a pen drive is not influenced by you buying a laptop, right? So now what we are going to do is we are calculating the probability of a person buying at least a laptop or a pen drive, right? These are mutually exclusive events, right? Can't happen at the same time, isn't it? Because what we are doing, at least a laptop or pen drive, right? Probability of, so as you can see from this particular example, right? You either buy a large shirt or you buy a small shirt, right? So probability of any sale is 0.01 plus 0.1 here out of 1000, right? If you take this, in the case of this particular example, you can buy them at the same time, both laptop and pen drive. But generally, when you're buying a shirt for yourself, you don't buy both a large size t-shirt and a small size t-shirt for you, isn't it? Right? So that's the reason why they are mutually exclusive, right? Again, simple difference. Mutually exclusive events cannot happen at the same time, right? Whereas independent events, the events can happen at the same time, right? As you and your friend going to the theater at the same time, but they are not dependent on each other, right? So because they're mutually exclusive, you can use the addition rule. You can just add up the probabilities, and then you say that probability of you buying a large size shirt or a small size shirt is 0.01 plus 0.1, which is 0.11. Okay, so that is the addition rule for mutually exclusive events. Okay, cool. So now with that, we come to the end of this recording. So this recording will stop here. I know it's probability, right? I want you guys to take a breather, right? Again, recollect what we have covered going to the PPT, right? Understand the terminology that we use. So this particular recording is more about understanding the probability concepts. Why are we learning probability concepts? Because we need to solve Sarah's problem. What is Sarah's problem, right? Whether she is in the top 1% or not, top 10% or not, right? For that, what we learned that probability theory is important, because for me to make inferences about Sarah, right, I need to understand probability theory, right? Because that is you in making inferences from looking at a sample, right? That's exactly what we're going to learn. And in probability, we understood how probability is calculated, what are the different concepts behind probability, what are all the possible values, denominator, numerator. We look at the simple example of throwing the number of dice. We saw probability distribution of an event, how the probability density function is shaping up, right? And then we also looked at importance of sample, right? Sample space, sample point. And then we started defining some terminologies like an event, an occurrence, right? Decision tree, independent event, two events happening at the same time, which are not dependent on each other. Dependent events, right? Events happening at the same time and they're being dependent on each other. Mutually exclusive events, two events happening not at the same time. Two events not happening at the same time, right? And then we also learned how do we use probability, right? Historical data to make predictions about the future, right? If somebody asks you what are the chances that you're going to buy 5 or more laptops, you will say 0 because you have never done that, right? And these are the rules of probability. Probability of any event lies between 0 and 1. Sum of probability of all possible outcomes is equal to 1, right? And then we also looked at, here we can't apply addition rule because these are not mutually exclusive, right? You buying a laptop and you buying a pen drive. So here you are unable to apply the mutual addition rule. But in this case, you are able to apply the addition rule purely because these two can't happen at the same time, right? Probability of large intersection small, right? You buying a large t-shirt and a small t-shirt, they are exclusive, right? They're completely exclusive. They can't happen at the same time. You don't buy t-shirts of two different sizes at the same time, right? So that's the reason why you can pretty much add the probabilities together, and then you say probability of either you buying a large or a small sale is 0.01 plus 0.1, which is 0.11. Okay, cool. In the next recording, we are going to complete the probability discussion by discussing about conditional probability, and we're also going to look at the most important distribution called normal distribution, and then we're also going to solve Sarah's problem. What is Sarah's problem? Sarah's problem is whether she is in the top 1% or not, right? We are going to solve that problem. We're also going to look in depth into the normal distribution discussions, which is pretty much the most important concept in the entire probability theory. Okay, cool. Hope you guys enjoyed this discussion. I know this is a tad different from the descriptive statistics discussion because that discussion is cakewalk compared to these concepts, isn't it? Right? It was fairly simple calculation of formulas, putting in values in descriptive statistics and making sense of the values. And here, you need to make sense of the formula, which formula to use when, right? What exactly is the concept behind the formula? That is more important rather than you just relying on formulas to show you the light. Okay, cool. In the next recording, we're going to look at conditional probability, normal distribution, and solve Sarah's problem. Until next time, have a good time.